Hi, thanks for joining me. Today I'm going to be going over problem 4 from the Imperial College Maths competition. As always, there'll be a link in the description below with details of the competition. This is a problem I'm going to be tackling today. We want to know, does there exist a subset of the positive rational numbers R such that every positive rational number can uniquely be expressed as the sum of elements in R? So R is just a set of positive rational numbers, and then it has the property that every single positive rational number, whether it's in R or not, can be expressed uniquely as the sum of elements in R. Now, one thing to note is this uniquely thing here is important, because if we didn't have the uniquely condition, then we could just have R being the set of positive rational numbers, and of course every single positive rational number can be expressed as elements, as the sum of elements in the set of positive rational numbers by just taking that number itself. But we want to show that, or we want to know whether an R exists such that we can uniquely express every positive rational number as the sum of elements in R. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into the solution. Okay, so the solution to this problem is no, such an R can't exist, and we're going to argue that by contradiction. So we're going to suppose for contradiction that such an R exists. Now, first thing to notice is that we can rescale all the elements in R. So firstly, R is non-empty, that's quite obvious. In fact, it's going to have infinitely many elements. And we can rescale the elements in R if we need to, so that 1 is an element in R. So if 1 isn't an element in R, that's fine. If 1 isn't an element in R, then we can always just say take an element T in R and multiply every element by 1 over T. So of course then we'd have a 1 in our set. And I'll leave that as a little sort of exercise to you to check that that won't affect the uniquely expressible property, so that every positive rational number can still be uniquely expressed as the sum of elements in R. Okay, so that's a little exercise for you, but we're going to assume from here on that without loss of generality, 1 is in R. Now I've got a little claim I've written up on the whiteboard. I claim that if x is bigger than y, with x and y in R, then x must be bigger than or equal to 2y. And we're going to prove this by contradiction. And once we prove this result, we can continue with our main proof in showing that R can't exist. Okay, so let's prove this. Or suppose x is less than 2y. So if x is less than 2y, but we already know that x is bigger than y, so we know that this thing holds. Well then, x minus y is going to be less than y, okay, from this inequality here, just minusing y from both sides. But notice x minus y is certainly a positive rational number, because x and y are in R, so x and y are positive rational numbers, and x minus y is going to be a rational number, and it's going to be positive because if I minus y from both these things here, I get x minus y is bigger than 0. So x minus y can certainly be expressed as the unique sum of elements in R. So there exists a subset y of R such that the sum of the elements in y gives me x minus y. But then notice that if I do, and also note, I probably shouldn't use y here, it's poor notation. Let's put t instead. So the sum of the elements, there exists a subset of Ry, a capital Y, such that when I sum all the elements in y, I get x minus y. But notice that little y here is not going to be an element in big Y, because big Y obviously sums to x minus y, which is less than y. So all the elements in big Y are going to be less than little y. So that means y isn't in y. But then if we look at the set y tilde, defined to be equal to y union y, well, if we sum up all the elements in here, what are we going to get? Well, we're going to get x minus y plus this y here, which is x. Okay, so we can write x in that way, but then we can also write x as just the element x itself. Okay, so we found two different ways. So we can either write this thing here, or we can just look at the set x by itself. Whenever we take any of these two sets and sum the elements in there, we're going to get x, but that's a contradiction because we know that every element in R can uniquely be expressed as the sum of elements in R. So x can't be less than 2y, so it follows that x must be bigger than or equal to 2y, and that proves this claim. Let me clean up the whiteboard and we'll continue with the proof. Okay, so now what we're going to do is consider the set R intersect the open interval 0, 1. So all the elements in 0, 1 that are also in R, and I'm going to call this set R1, R2, R3, and so on. Now, by the lemma we just proved, we can show, or sort of a corollary from that, is that any open interval of the form AB, where A is strictly bigger than 0, any interval of this form will only contain finitely many elements of R. And now that's just a sort of corollary of the lemma we just had. But in fact, this set here is going to have infinitely many elements, and that doesn't contradict this thing here, because here our A is 0, which is not strictly greater than 0. Anyway, we've got infinitely many elements in this set here, and in fact, without loss of generality, we can order them sort of by this property here, because if we look at any sort of, if we look at any subset of this, which is of the form epsilon 1 intersect R, then this is only going to contain finitely many elements, so it makes sense to order this. So without loss of generality, we have that R1 is bigger than R2, is bigger than R3, is bigger than, and so on. Now, one thing I claim is that R1 must be less than or equal to a half. Why is that the case? Well, because if R1 was greater than a half, then it equals, let's say, half plus epsilon, where epsilon is also between 0 and a half. But then we know that 2R1 is going to equal 1 plus 2 epsilon, but in particular it's going to be greater than 1. But remember, we just, from the lemma we just had, if we know that then R intersect this interval here, R1, 2R1, is going to be empty, but this contradicts the fact that 1 is in R1. Okay, so by the lemma we just had, R intersect R1, 2R1 must be empty, but we know that the element 1 must be in this set here, so that's a contradiction. So we must have that R1 is less than or equal to a half, and for the exact same reason, R2 must be less than or equal to a quarter, R3 must be less than or equal to an eighth, and so on. So in general, Rn must be less than or equal to 1 over 2 to the n. And now what I'm going to do is argue that in fact each Ri must be exactly equal to 1 over 2 to the n. So we've shown that Rn is less than or equal to 1 over 2 to the n, but now I'm going to show that in fact it can't be strictly less than. So let me bring this up to the top of the whiteboard and we'll continue. Okay, so we just showed that each Rn is less than or equal to 1 over 2 to the n, and now I claim that in fact Rn has to be equal to 1 over 2 to the n, and we're going to prove that by contradiction as well. So there are a lot of proof by contradictions in this argument. Okay, so suppose for contradiction there exists some positive epsilon and some natural number m, such that Rm equals 1 over 2 to the m minus epsilon for some m in the natural numbers. Well then, just let q be a rational number, but also in the interval 1 minus epsilon at 1. Okay, so this is going to be a very small interval, and in fact when we intersect it with the rationals it's going to be even smaller, but there's still going to be infinitely many rational numbers in this interval here, so just pick one of them, and we're going to show that we can't ever attain q. So firstly, q has to be sort of from these ri's here, because the next biggest element in capital R is going to be 1, but if we have 1 in our sort of subset making q, that's already too big. Okay, so we have to have q is the sum of our m, so q then equals the sum of some subset of these Rm, so some, let's denote it like this, I, a member of I, of Ri. Okay, but this is going to be less than or equal to if we just add them all up, so add up all the i's, Ri's, so, okay, like so. So all I've done here is I know that q is going to be the sum of some of these Ri's, where each of the Ri's we know are less than or equal to 1 over 2 to the I, okay? But that's going to be strictly less than if I just add up all of them. But then I know that this thing here is going to be less than, it's going to be less than or equal to the sum from n being greater than or equal to 1 of, and without looking at the nth case, of just 1 over 2 to the n. And then adding up the nth case as well is plus 1 over 2 to the m minus epsilon. But I know that this thing here just sums to 1 minus epsilon. So I get that q is less than or equal to 1 minus epsilon, which is a contradiction for this thing here. So I essentially proved my claim that Rm must be equal to 1 over 2 to the m for every natural number m. Okay, so we know that all the elements in R that are less than 1 are sort of reciprocals of powers of 2, and now we can almost arrive at the desired result of our contradiction to show that a capital R can't exist. Okay, so we're at the last step now. We've shown that R intersect 0, 1 is this set here, the reciprocals of the powers of 2, and now I claim that a third, which is clearly a positive rational number, can't be expressed as the sum of elements in R. And to see that, firstly, if we were to be able to sum a third as the finite sum of elements in R, all of those elements must come from this set here, because if we try and add an element bigger than 1 that's in R, then we're already going to be too large for a third, because a third is strictly less than 1. Okay, so a third we're supposing can be equal a sort of a finite sum of reciprocals of powers of 2, but that leads to a contradiction, and there are a few different ways you can see that, but I think the easiest way to see that is we know that a third, if you write it out, is 0.33333, and so on. But we know that any power of 2, or the reciprocal of a power of 2, only has a finite number of decimal places, and I guess you can prove that sort of by induction. So a half is 0.5, a quarter is 0.25, and so on. So any finite sum of powers of 2 is only ever going to have a finite number of decimal places, so it can never equal a third, and there's our contradiction. I guess another way you can do this is you can write what a third is in base 2, and then show that it can't be expressed as a finite sum of elements in R. Anyway, that's the contradiction arrived, and that solves our problem. Sort of a lot of proofs by contradictions in our argument here, a lot of sort of mini lemmas to get to this final result, but there is a solution. In fact, there's a couple of other ways you can solve it as well. Anyway, thanks for watching. I will catch you in the next one. Have a great day.